Welcome back. So we talked about relative age. This compared to that is older or younger. We talked about geologic age, fitting things into kind of chunks of time throughout geologic past. And then we also can date things with something called absolute age, putting an exact number on it. This rock is 220 million years old, so putting some value on it. Now, if you remember, right, the Earth is 4.54 billion years old. It's hard to imagine that. You know, we've heard billions, right? People have billions of dollars. Well, how much is that really? So let me give you a little kind of just reference. So imagine if 1 year was represented by just 1 second. All right, so 1 year is equal to 1 second. All right, so therefore 100 years, that would be 1 minute and 40 seconds. All right, 1,000 years would be 16 minutes and 40 seconds. Okay, 10,000 years would be 2 hours and 47 minutes. 100,000 years would be 1 day and 4 hours. 300,000 years, this is when modern Homo sapiens, humans, evolved. That equates to 3 days and 11 hours. A million years is equal to 11.5 days if 1 year is a second. A billion years is 31.7 years if 1 year equals 1 second. There's a big jump between a million of things and a billion of things. So when we're talking about the Earth being 4.543 billion years old, the age of the Earth, that would equate to 144 years. So whereas humans evolved, if we're talking about right now is current, and we're representing all of geologic time in this scale, just to give you a sense of how immense it is, then if right now is now, then 3 days and 11 hours ago, that's when humans first evolved, but yet the Earth formed 144 years ago. Think how large that is. Let me help you visualize it. So here's money. Here's $10,000. Here's $1 million. These are all stacks of $100 bills. There's $1 billion. There's a big difference between, 10,000 and a million. That sounds like if I said, would you rather, what's a bigger difference, 10,000 and a million or a million and a billion? People's brains automatically, well, 10,000 is low and a million is so much. A billion is so much, therefore a million and a billion, they're both so much, they're kind of similar. Therefore $10,000 is small compared to a million. So that's the bigger difference, 10,000 and a million. There's a bigger difference between a million of something and a billion of something. So when we're talking about the absolute age of the Earth, we need to understand just how long the Earth has been around. And it's hard for us to wrap our brains around that. But this kind of hopefully gives you some sense of idea. If we were to represent all of the geologic time scale past 4.54 billion years in a stack of land, this is what we would see. All right, kind of breaking it down. So again, the solar system forms 4.54 billion years ago. All of these things that have occurred through time, number of different things, and here's the top of that. You can see that Homo sapiens, humans, occurred in this scale about 0.2 million years ago, so about 200,000 years ago. So 300,000 years ago. That's really nothing as far as Earth is concerned. Right? Yeah. Dinosaurs, if I go backwards here, dinosaurs are kind of right here on this scale, and there's still just so much time that came before that. We think, what happened a long time ago? Dinosaurs. Actually, dinosaurs are much closer to humans than they are to the beginning of Earth. Way closer. Way closer. So, just some interesting things to think about. So again, how old is the Earth? But how do we know? All right. So the Earth, again, 4.54 billion years old. How do we know? I've mentioned it to you, but here's how we figured it out. Going back to some early attempts at dating Earth, just as a few different examples. Sir Edmund Halley, famous for Halley's comment. 1715 suggested, you know what, let's calculate the age of the Earth based on the rate of salt accumulation in the ocean. How much salt is in the ocean. If we can kind of figure out at how fast that process occurs, we can go backwards and figure out how old the Earth is. It was just suggested at this point. He didn't actually do it. Jump a little bit ahead. Charles Darwin, famous for the theory of evolution. Remember, theory, highest level of knowing. Testable, repeatable, never been proven false. He believed that evolution, a slow process, which it is, Earth had to be at least 300 million years old. So that's still way short of 4.5 plus billion, but still putting an age on the Earth that went well beyond what, most religious texts alluded to, Earth only being in the thousands of years old. They were a little off. Lord Kelvin, Lord Baron Kelvin, if you've ever taken chemistry and worked with the Kelvin degree scale, that's the same person. So he used the law of thermodynamics, little physics, to calculate the length of time needed for Earth to cool to a solid body. Again, assuming that Earth started off as a molten hot ball of craziness, which it did, how long would it take that to cool down? And using his calculations, which were a little off, he came up with 20 million years. Again, that's a far cry from 4.54 billion, but still putting values in the millions of years as opposed to just merely thousands of years. 1889, John Jolly, fun name, took Halley's idea from 1715 and derived the Earth's age of 90 million years old. But then came along something in 1905 called radiometric dating. Radiometric dating. A lot of material has small amounts of radioactive elements in it. For instance, if we look at a piece of rock, a granite, for instance, which is a type of rock, more on that in another unit, there will be small amounts, very, 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 very small amounts of uranium. Over time, uranium decays, radioactively decays, to become something else. So what we do is we look at a rock and we can count how many uranium atoms there are versus how many atoms that it breaks down to, which in this case would be lead. If we can compare those two and we understand how fast uranium decays to lead, Pb stands for lead, then we can, just by knowing that ratio, we can figure out how old the rock is. All right. So we would refer to uranium in this case as a parent atom. It's unstable, our parent isotope, and then it decays to form its daughter product, daughter atom, in this case lead. So again, if we know the rate at which that happens, we can calculate how old a rock is based on counting how much uranium is in there and how much lead is in there. And we count it using something called half-lives. So let's say you have we're looking at a rock and we're looking at the parent atoms, the parent isotopes, and we see there's all uranium, there is no lead in there. Okay, well, it's gone through what's known as 0 half-lives. A half-life is the amount of time it takes for a parent to decay, half of the parent to decay to the daughter product. So if there has been no decay, it's 0 half-lives. Half of it has not decayed yet, has not changed from a parent to a daughter. All right. So in this case, there's 32 parent isotopes, 0 daughters, so 100% parent, 0 daughter, no half-lives. So again, a half-life is the amount of time it takes for half of the parent isotopes to decay to daughter products. So after 1 half-life, there will be 50% parent isotopes, 50% daughter. Half of it decayed. So that would be 1 half-life. If that happens again, so if another half of this 50% decays, that would drop it down to 25%, thus increasing the daughter product to 75%. That's undergone 2 half-lives. And there are a number of different radioactive isotopes and atoms which we understand the rate at which they decay. We understand their half-lives. In doing so, and counting parent and daughter products, we can start to calculate out how old something is. So again, as the percentage of parent isotopes or parent atoms decrease, the amount of daughter isotopes or atoms increase. All right. So, for instance, uranium-235, this is a very common parent isotope, a parent atom that we count. One half-life of this we know to be 0.704 billion years. So after that amount of time, half of the uranium in a rock will decay, making the other half the daughter product. So one half-life, if we're looking at a rock and we're counting, this has exactly half uranium and half lead in what we can count. Well, that means it's undergone one half-life, so it's 0.704 billion years old. So 704 million years old. If we count two half-lives, we know it's 1.4 billion years old. Three half-lives, 2.1 billion years old. Four half-lives, 2.8 billion years old. It just depends on the ratio of what we're counting. Five half-lives, 3.52 billion years. So we know the half-life, the time it takes for half of the parents to decay to these daughter products. We know that for different atoms and different isotopes. I'm not expecting you to memorize or understand any of what these are, but there are certain elements we know how fast they decay. And what they decay into, if we just count them using very fancy, very expensive machinery, we can calculate the ages of rock. You look at any rock, figure out what's going on, count the half-lives, we know it. Again, it's complicated, more complicated than that, takes some advanced machinery, but the basics of it, that's how it goes. For more information on how radiometric dating works, watch this. All right, it gives you a little bit of additional detail, a little bit different look at it. So please watch this link. Before I sign off, we'll pause here. We'll finish up this section in the next video. But before I do, let me give you this part of the super secret code. It is the number 526. You got me? 526. One more time. 526. All right. So we'll pause here. When we come back, we'll continue talking about absolute age. See you back here in just a minute.